You pull into a bay, grab the nozzle, and fill your car in seconds. It is an incredibly mundane routine. You pay, you drive away, and you rarely consider the mechanics of what just happened. But the fuel flowing into your car is an active chemical threat. Early vehicles ran on kerosene, which has a flash point of 38 degrees Fahrenheit. It remains relatively stable until it gets hot. Gasoline, however, has a flash point of -40 degrees. At room temperature, kerosene sits quietly, while gasoline constantly emits a cloud of highly explosive, invisible vapor. Early drivers often failed to respect this volatility. To get fuel, you would walk into a hardware store where an employee poured it directly into a metal can, right next to the saws and kettles. The customer then took that can outside and poured it into their car using a simple funnel. When early engineers tried to scale up delivery, they built visible above-ground fuel pumps. An attendant hand-cranked gasoline up into a large exposed glass tank right on the side of the city street. From there, gravity drained the measured amount down into the car. Storing massive volumes of constantly vaporizing liquid in glass cylinders near busy city traffic was catastrophically dangerous. Taming a chemical where a single stray spark could trigger a localized disaster required burying the problem out of sight, relying on a massive architectural system hidden beneath our feet. In 1913, the Gulf Oil Company opened a dedicated fueling station in Pittsburgh. To avoid the traffic jams and obvious fire hazards of curbside pumps, they moved the massive storage tanks entirely underground. Those early tanks were made of steel, which would inevitably corrode and leak raw gasoline into the surrounding soil. Modern stations solve this by burying massive double-walled fiberglass tanks that prevent structural decay. Look at this cross-section of a modern underground tank receiving a delivery. To prevent a spill, engineers built an exact mechanical failsafe. As incoming gasoline reaches exactly 95% capacity, a flapper valve flips up, instantly stopping fuel flow from the truck. But filling the tank creates an invisible problem. As thousands of gallons of liquid gasoline rush into the confined space, the highly flammable layer of vapor already inside the tank gets pushed upward, threatening to vent directly into the atmosphere. To prevent an explosion, the displaced vapor is forced out through a secondary dedicated valve at the top of the tank. It travels through a separate pipe and is routed straight back into the delivery truck to be safely recycled. The underground gas tank operates as a dynamic, closed-loop pressure management system, neutralizing explosive gases before they ever reach the surface. When you squeeze the trigger on the pump, a submersive inoter at the bottom of the tank activates. It pushes the liquid gasoline up through a series of specialized filters, straight into the surface dispenser. For decades, an attendant managed this final step. When Frank Olrich opened the first self-service station in 1947 to lower gas prices, it created a mess. Untrained drivers had no reliable way to know when their tanks were full, leading to dangerous spills all over the concrete. Engineers needed a way to cut off the flow of fuel automatically. The solution they built relies on zero electrical sensors. It is a purely analog masterpiece. This cross-section shows the interior of a modern nozzle. As fuel is forced through a narrowed opening inside the handle, its speed increases. This physical property, fluid moving faster through a tight space and dropping the surrounding pressure, is known as the Venturi effect. That localized pocket of low pressure actively sucks outside air into the system. It pulls this air in through a tiny hole located right at the tip of the metal nozzle, routing it up a thin secondary tube to mix with the flowing fuel. As the liquid inside the car's gas tank rises to the top, it eventually covers that tiny hole at the tip of the nozzle. In a fraction of a second, the nozzle's air supply is completely suffocated. With the air path blocked, the continuous suction has nowhere to pull from. It instantly creates a sudden vacuum inside a small sealed compartment in the handle, pulling a flexible membrane upward. When that membrane lifts, it releases a set of small holding ball bearings. Without those bearings keeping the structure rigid, the internal lever system collapses and the main fuel valve snaps shut. The handheld nozzle is an analog fluid dynamics computer. It utilizes the raw physical pressure of the fuel itself to outsmart human error and stop the flow of gasoline instantly. Back on the surface, you hear a heavy click, return the nozzle, and drive away. The entire mechanical ballet of pressure vacuums, ball bearings, and vapor routing happens invisibly beneath you. Multiply that interaction across the world. Every single day, these mechanisms safely process and pump out 3 billion gallons of highly volatile fuel. Engine efficiencies are improving, and the overall number of gas stations is slowly declining as cars require fewer trips to fill up. But the engineering footprint beneath the concrete remains a vital piece of modern infrastructure. Over the last century, engineers took a chemical with a flash point of -40 degrees